Previously, we had started with a intuitive definition of force and went ahead to look at some different common kinds of forces. I'd now like to transition to discussing how forces cause motion to happen. This has been codified by Isaac Newton. Interestingly, while he was hanging out back at the family farm, waiting out a pandemic in his era, he got to thinking about how motion actually happens. And not all of the thoughts here are completely original to Newton. Some parts of his laws of motion had already been formulated by other workers such as Galileo. However, it was Newton who put it together into a comprehensive form that didn't have any gaps. So with that, I'll go ahead and state the first of the three laws of motion that he came up with. And I'm presenting it to you in English translation from his text, the Principia. Newton actually wrote it in Latin because back in that time, it could be expected that any educated European scholar would know Latin. Just like today, it's pretty much the case that almost all physics literature is published in English because you can expect that most, if not all, researchers in physics have at least some familiarity with English. So anyway, I like going with Newton's original statements, mostly because a lot of the textbook statements, in an attempt to make them clearer, miss little nuances, and some of those nuances are important, especially with the second law. So we'll start with the first law here, and this one states, every body perseveres in its state of rest or of uniform motion in a straight line, unless is compelled to change that state of forces by forces impressed thereon. Okay, so what does this do? It actually defines three things. First thing it defines is the concept of inertia. So what do we mean by inertia? What we mean is, what is the natural state of affairs for an object to be doing? Up until sometime maybe in the 60, 70 years preceding Newton, it was pretty well held that the quote-unquote natural state of affairs for an object would be to stay at rest. However, it turns out that that isn't going to work. Turns out what Newton found is that what Newton states here, based on synthesizing observational data up to this point, says actually the natural state of affairs for an object to move at a constant velocity. And again, that this is the natural state of affairs for an object. So what do I mean by this being the natural state of affairs? Well, what this would mean is that at the risk of anthropomorphizing an object, we would say that what it wants to do, or what any object will just inherently do, is to move in a straight line at a constant speed forever. That's hard to do in practice. You can see this sort of thing in deep space. But in practice, and this is probably what makes Newton codifying the first law so remarkable, in practice, it's almost always the case that there's something interfering with this natural state of affairs. So for him to tease out that this is the natural state of affairs for an object is itself pretty remarkable. And what interferes with it, with this natural state of affairs? What will cause an object to change its velocity? That, Newton says, is a force. In fact, we can take this as our definition of a force, as being that thing that will cause an object to change its velocity. So we'll define a force as that interaction which changes an object's velocity. So, for instance, in space, you think, okay, things seem to go in straight lines at constant speeds forever, right? Yeah, but let's say we're in the vicinity of the solar system. You can go look at some comet or something like that, and what you'll see that comet is actually doing is taking an elliptical orbit around the sun. Depending on the class of comet it is, this orbit could take billions of years to complete, or on the order of a billion years or so to complete, but it's not moving in a straight line constant speed, and the reason for that is the sun is exerting a force of gravity on the comet to change its motion from the natural state of affairs of a straight line at constant speed to something else. Okay, now tied into this more subtly, Newton gets into it more in his discussion of the first law in the Principia. But we've already kind of touched on this a little bit when we brought up reference frames in two-dimensional kinematics. And this is that also defines an inertial observer. And so this is an observer who in Newton's framework is allowed to quote-unquote do physics. What do I mean by that? So an observer who can quote-unquote do physics. So for instance, we can imagine a situation where, say, we have a person on a skateboard. Like so. Oops, skateboard better have some wheels. And our skateboarder is moving down the road at a straight line, constant speed. The skateboarder tosses a ball. Now, you, standing on the side of the road, watching the skateboarder go by doing this thing. So let's put some grass around. There we go. You stand by watching the skateboarder do this. You observe the trajectory of the ball, and you say it's a parabola. And you conclude that it's a parabola because the Earth is trying to pull it straight down, and so thus it has an acceleration straight down. And we've seen that if we have an acceleration that's always of constant magnitude and direction, that the trajectory of such an object is a parabola. And the skateboarder, on the other hand, is going to say that the ball is going straight up and down. Now, you're both right. And we can even just go into the really technical case of saying that straight up and down is a really strained, limiting case of a parabola. But we don't even need to go there. We can just say, from your perspective, the person standing by the side of the road, you would observe that the skateboarder's velocity in the x direction is the same as the ball's. And so you would conclude that the skateboarder will never measure a change in how far in front of them the ball is. And so thus you would conclude that they would conclude that the ball goes straight up and down. Now, the skateboarder can take the other perspective. Since there actually is no proper experiment and this is what Newton's first law assures us, is that there is no proper experiment that the skateboarder can do to tell that they're the one that's really stationary. For all they know, they were put into some room with an elaborate computer simulation running, and you and everything's on like some giant treadmill, something like that, or a conveyor belt, and everything's moving past them. Now, we look at that and we go, that's kind of pushing it. But really, there is no experiment that can be done by the skateboarder to tell that they're the one moving. So as far as the skateboarder is concerned, they're stationary and you're the one moving to the left. And so they would say, well, I threw the ball up and down, but you are constantly seeing a varying x coordinate because of your motion. So although the ball is going up and down, I know that you would see it as a parabola. And you could be led to then ask, well, who's right? And what Newton is telling us in this more subtle bit of the first law is that you're both right. So that's the three things that Newton's first law does for us. It defines inertia. And it tells us that the natural state of affairs of an object is to move in a straight line at a constant speed forever. It operationally defines a force as being that thing that changes an object's motion from that natural state of affairs. And then finally, it defines the inertial observer as being someone who's moving at a constant velocity. They're allowed to say that they're the one stationary, the whole rest of the universe is moving around them, and they can translate back and forth between what they see and what some other inertial observer sees. Later workers, as an aside, have actually taken this idea a step further and said, really, you ought to be able to formulate physics in a way that all observers, not just inertial ones, can quote-unquote do physics. And this is a framework that was put forward by an extension to the Newtonian framework that was put forward by a physicist by the name of D'Alembert. And this sort of idea ultimately extends into Einstein's theory of general relativity, which is our current best model of gravity. But right now we're working in Newtonian mechanics, and so we say that inertial observers are allowed to quote-unquote do physics. Now, if our skateboarder were accelerating in Newton's framework, they would be able to conclude that yes, indeed, they were the one who was moving because of their accelerated motion. So, for instance, if you're driving around a corner and you have, say, a parking pass hanging off of your rear view mirror, as you go around the corner, you'll notice that the parking pass changes its angle. And this is a way that you can conclude that you are the accelerated observer, that you're the one accelerating around the corner. And so for that time when you're going around the corner and your velocity is changing by virtue of the fact that you're changing your direction of motion, during that period, you can conclude that you are not an inertial observer. But during any stretch where you're going at a constant velocity, you are perfectly entitled to say that you are the one that's stationary and the whole rest of the universe is moving around you. And that's what Newton gives us as the third consequence of the first law. Okay, so with that, let's go ahead and introduce his second law. The third law of motion will wait for a later video, just because there's enough subtlety and trickiness to it that it deserves its own video. But let's go ahead and state Newton's second law and explore what that means. So again, going with the English translation out of the Latin that Newton wrote, the alteration of momentum is ever proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. Okay, that's a mouthful. And unfortunately, that's the case for Newton just in general. I will say that his writing style is very much of the why use 5 words when 40 will do almost as well. But he was trying to be very careful and very precise. Nowadays, we would write this more mathematically. So the correct statement of Newton's second law, and I'm going to have to explain what I mean by saying it's the correct statement in a moment, is to say that it is the result of net forces being applied to it. Remember, net force was just the vector sum of all the forces acting on an object, will be equal to the time rate of change of the momentum of an object. So again, remember, this is a derivative here. So this is a limit as our time intervals approach 0 of the change in momentum over the change in time. So this lowercase p is a symbol for a quantity called the momentum. And since we have to start somewhere, we haven't actually defined this yet. So we'll have to wait a while before we can use the full-blown version of Newton's second law. However, it turns out that in what amounts to virtually every case you're ever going to practically concern yourself with 2 notorious exceptions, this can be rewritten as saying that the acceleration of an object is equal to the net force applied on the object over the object's inertial mass. Whoops. Here, let's do this. There we go. Now, this is a limiting case version of the correct statement, which is F net equals dp dt, where p is this momentum we haven't defined yet. However, as long as 2 conditions are met, this expression is fine, and these 2 conditions are met most of the time. The first condition is that the object's mass be a constant. There are 2 notorious exceptions to this. One of the classic examples is, say, a raindrop falling down. As a raindrop falls down, it picks up additional water molecules out of the air, and its mass increases as it falls down. Or the flip side is if you're launching a rocket, roughly about 90% of the mass of a rocket is fuel, and that fuel burns down very, very fast. And so the mass of a rocket changes very rapidly. And in addition, because of technical issues having to do with rocket motor design for operating in an atmosphere versus operating in a vacuum, manufacturers of rockets generally have to make one rocket motor that's optimized for operation in the atmosphere and another one that's optimized for operation in a vacuum. And so they usually build the rocket into at least 2 stages. The first stage has the atmosphere optimized rocket engine, and the second stage has the vacuum optimized design. And so what you do is at a sufficiently high altitude, usually somewhere around about 100 kilometers, you literally just throw away the first stage of the rocket. But in so doing, you lose additional mass when you do that. to do this, to handle this, it turns out that you will have to go back and use the correct version, this one here, that the net force equals the time rate change of the momentum. And we're going to have to do some calculus to ultimately come up with Solovsky's rocket equations to describe that kind of motion. The second case is that, the second condition here is that the motion be non-relativistic. What I mean by that, that means that the speed of the object, of all the objects involved, has to be substantially less than. So remember, less than just means much less than. The c, which is the speed of light, which is just a shade under 3 times 10 to the 8 meters per second. And so as long as you're doing that, again, and your mass is a constant, we can just turn F net equals the time rate change of momentum into saying the acceleration is the net force applied on an object over the object's mass. If an object is moving at relativistic speeds, it'll turn out that the definition of that because of a relativistic correction to the definition of momentum, this second form that I have boxed here won't work for us, and we'll have to go back to using the first form where we say F net equals the time rate change of momentum. But we won't run into doing relativity until we've done a treatment of electricity and magnetism. Okay, so the force does have its own units. The SI unit of force is the Newton. This is what we call a derived unit. It's defined to be 1 kilogram meter per second squared. And if we look here, we can see, yeah, the acceleration is meters per second squared. Whatever the units of force are, I would have to divide them by kilograms to get meters per second squared. So that forces the units of force to be kilogram meters per second squared. And it is perfectly legit to just write kilogram meters per second squared, but you do that so often that we usually prefer to write a capital N as an abbreviation for that and refer to it as a Newton of force. Similarly, the standard American equivalent unit of force, or the old British traditional unit of force, is the pound. The unit of mass, by the way, is the slug. And a pound is a slug foot per second, or a slug foot per second squared, if you prefer. Okay, so let's just go and take a look at how this ties together. Let's just do one quick example of how this, of just getting an acceleration. Let's just say you're pushing on a box. Let's say your box has a mass of 2 kilograms, and let's say you're applying a force of 10 newtons. To the right, I'd like to know what is the acceleration equal to. Well, I can get the direction of the acceleration immediately. It also has to be to the right. And this is by Newton's second law. We can say the acceleration is the net force over the mass. And so if I just, to just make this a little more explicit, we can kind of rewrite this as 1 over the mass times F net. 1 over the mass is always going to be a positive number. So I'm taking my net force, the sum of all my forces, and I'm multiplying it by a positive number. So the acceleration of an object has to point the same way. Here, I'm imagining that we must be in deep space or something, but I'm just pushing, so there aren't any other forces other than the force of my push. I'm exerting a 10 Newton force on it for as long as I'm pushing on it. So it will accelerate in the same direction as my push in this example. So to get the magnitude, we can just drop the vector signs and say the acceleration is F net over the mass, which will be just my one and only force over the mass. So that's 10 newtons over 2 kilograms. Let's just double check the units here. So this would be 10 kilogram meters per second squared over 2 kilograms. Yep, cancel, cancel. And 10 over 2 is 5 meters per second squared. So then we could ask ourselves what would happen if, say, the box, instead of being 2 kilograms, was 5 kilograms. Well, if the box was 5 kilograms, the acceleration would now be 2 meters per second squared. So let's just go ahead and revisit that thought here. So we will take my 5 kilogram box, or my 2 kilogram box now, and make it a 5 kilogram box. And again, the same 10 Newton force. Again, it'll accelerate to the right. So I can again get that the acceleration, the magnitude of the acceleration is F net over m, just F over m. So this will be now 10 newtons over 5 kilograms. We get that it's 2 meters per second squared instead of 5. So for the same push, the acceleration is lower. And we could continue to take this a little further along. If I push on a 10 kilogram box, the acceleration with the 10 newtons force, the acceleration would be 1 meter per second squared. If it became a 100 kilogram box, it would be 1/10 of a meter per second squared. Let's say I push on a metric ton, 1,000 kilograms. Now we're talking 0.01 meters per second squared. Let's say it's 1,000,000 kilograms. Then we're talking 0.00001 meters per second squared, etc. So by the time you get to like the mass of the Earth, if you were to push on the Earth with a 10 Newton force, just say when you're pushing your foot off while you're walking or something, you know, like maybe just decide to take a quick little hop or something like that, pretty much whatever force you exert on the Earth, you are indeed causing the Earth to accelerate. However, you're not causing it to accelerate by very much. I kind of did the math on it for just a typical person doing just a typical jump. They do indeed displace the Earth from its orbit for the time period where they are out of where their feet have left the ground. But it works out to be a fraction of a width of a hydrogen atom. But even at that scale, exerting a 10 Newton force on the Earth does indeed accelerate the Earth. Of course, there's probably somebody else on the other side of the Earth who's pushing with 10 newtons the other way, so, you know, hey, there you go. Alrighty. Now, one of the other uses of Newton's second law here is, say, when we have kinematics situations, or situations that look kinematic-y, but we don't have enough information. So let's go ahead and say that you're pushing a 2 kilogram box again. Like so. Let's say you're pushing it to the right like that. We'll say that you're exerting, let's say, a 5 Newton force this time. We'll say the box initially starts at rest. You're doing this all in outer space just because we have to start somewhere, so no other forces. And let's say you push it for 2 seconds. So I want to know 2 bits of information here. One thing I would like to know is, at the end, how fast is my box going? And the other thing I'd like to know is, how far did it move in these 2 seconds? So we've pretty much defined our situation here following the STAR model, Situation Tools Answer Review. I'm pretty much always allowed to set my initial position to 0, so I'm going to do that. So asking what the change in position is the same difference now as asking what is the final position. So this is the first example of a strategy that I like to call think backwards, solve forwards. What do I mean by that? So in the tools process here, when the difference between thinking about how to solve a physics problem and then actually doing the solution versus looking at a written solution is when you look at the written solution, they often start with just some seemingly random thing, some seemingly random observation that everything falls out from there. What doesn't often get shown in written out solutions is the behind the scenes thought process to get there. So I'm going to try to show that here. So when I go and look at this, my first instinct would be, hey, we're asking for final positions, final speeds. For the tools in my toolbox, that sure sounds like kinematics. So we can go ahead and write down what we know, and we know that the time elapsed is 2 seconds, and we're being asked for both the final position and the final velocity. Ooh, well, that's not the end of the world, because I could say use the missing x equation to get v, and I could use the missing v equation to get x, but the problem is I don't know the acceleration either. So then you kind of curse your lot in life and go, crap, I need to somehow get the acceleration. So then you go rooting around in your mental toolbox and ask yourself, is there some way that I could buy myself the acceleration so that I could then go and plug that into my kinematics to get a solution? And you say, oh yeah, sure there is. I could use Newton's second law of motion. So we're looking for the acceleration so I can then plug it into the kinematics, but we're given that we're exerting a 5 Newton force and that the mass of the thing is 2 kilograms. And now I look at this and this is all good because there isn't anything else unknown to get the acceleration. And then once I have the acceleration for Newton's second law, I can plug that back into the kinematics relations to then solve for what I need. So this is the think backwards process. We started at the final step of the process, doing kinematics. Found that in order to do that, we had to do something first, which is doing some acceleration, doing some Newton's second law stuff. So this is the think backwards part of this. And now we can go ahead and in the answer phase, we can proceed to solve forwards. So we start with what we finished off at the end in our thinking process. We start with Newton's second law now. We say, okay, the acceleration is the net force over the mass. So we're solving forwards now. And all the actions happening in the x direction. This is a vector equation, so I'll just go and take the x component. And if I look at my diagram here, I know from Newton's second law that the acceleration has to point the same way as the net force. In this case, there is only one force. So the two of them have to point the same way, which is the x direction. So the x component of my acceleration is just going to be a. The x component of my net force is just going to be my one and only force, which is my applied force F. All right. So since I wasn't asked for the acceleration, I'm in the interest of minimizing round-off error, I'm not actually going to go ahead and work out that it's 2.5 meters per second squared. But if you were asked that, you could certainly go ahead and solve for that, but then I would recommend that you store that result into your calculator's memory in order to preserve as many digits as possible to reduce round-off error. So now we can go and do some kinematics. So say, let's start by finding the final velocity. So at this point now, we have the, we're missing the final position, so we'll use the missing x. So that's what's neither asked for nor given. It'll be asked for very quickly, but for the purposes of this, since we don't know it and we do know the other things, we'll start here. And we can say, all right, the missing x equation says the final velocity is the initial velocity plus the acceleration times the change in time. Oops, sorry. Yeah. Now here we can go ahead and put in our zeros right away. The initial velocity is 0. And now for the acceleration, we can get what we solved here looking at Newton's second law and plug it in over there. So I end up with an expression that my final velocity is F over m delta t. So now I can put in the numbers, 5 newtons over 2 kilograms times 2 seconds. Okay, a newton is the same thing as a kilogram meter per, kilogram meter per second squared. The kilograms cancel, 1 power seconds cancel, so we're left with just meters per second. And 5 over 2 times 2, hey, that's 5 meters per second. So I have my final velocity is 5 meters per second to the right. Okay, now let's turn around and do the next bit and find the final position. So here, we look at this and we realize that nothing's missing. And that can happen sometimes. We have an expression for the acceleration, not that we ever bothered to solve for it being 2.5 meters per second squared, but we have an expression for the acceleration. That's good enough. We now have the final velocity. We have the we have the time elapsed. So we can use any of the equations that are not missing the final position. Any of them will work. I'm going to pick the one that's missing acceleration and just say, all right, and just because it's the one I feel like, I could have picked any of the others. This will be x initial plus 1/2 v initial plus v final delta t. X initial is 0, v initial is 0. So we get that my final position here is 1/2 times 5 meters per second times 2 seconds. Units work. We have meters, and 1/2 times 5 times 2 is 5 meters. Okay, so now we're into the review process. The units check. We were checking that as we went along. And the answers don't seem totally out of the realm of reality. Something going at 5 meters per second seems totally plausible. And so does it moving 5 meters in 2 seconds. So we'll go ahead and say that's plausible. And so that checks out there. So to recap, the big strategy wrinkle here is when we have to integrate more than one idea in solving a problem. I recommend the process of starting from pretending that you've almost found the solution, and you think about what the very last step was to get that. That's usually the thing that's sitting out there. In this case, it was, this sure looks like a kinematics problem, but then you realize that you don't have quite enough information. In this case, you realize that you didn't have the acceleration. So then you have to go back up and say, okay, in order to do that, I first have to figure out the acceleration, and I do have enough information available to use Newton's second law of motion to get that. Then this is the bit that you see in worked out solutions in textbooks and solution keys and stuff like that, is where they start with this last step of the reasoning, where you finally realize that you had enough information to do the problem. They just start you here. And we go ahead and solve forwards. We get the acceleration, or at least an expression for it. And then we insert that into our kinematics to then get us what we need for the to do the other parts of this. So that's the think backwards, work forwards thing. I would say, if you're looking at a solution key to something, trying to understand what they were doing, a lot of times it helps just to start at the back side of it and kind of work your way to the front, because that follows the actual reasoning process that the person who wrote the solution was following. Alrighty, so in the next video here, we'll be taking a bit of an exploration further into mass, since that was something that got brought in by Newton's second law. So we'll catch you in the next video.